Okay, let's take a look now at sections 4.3 and 4.4. These are pretty straightforward sections, and probably you could read them for yourself and wouldn't necessarily need someone to say it out loud. But we're looking at ordinary old graphs here. And the first definition, we got a lot of terms, and none of them are very difficult, but there are a whole lot of terms here. A path between two vertices. The two vertices are V1 and VR. And a path between two vertices it's a finite sequence of edges and vertices pardon me. A finite sequence of edges and vertices of the form. Okay, so V1 is where we start. Then we have an edge 1 that takes us to V2, then an edge 2 that takes us to V3, up to we have VR minus 1, and then the edge here we're going to call R minus 1 as well, and goes up to VR. Okay. Where when we write something like E sub k, it's the edge between vertex k and vertex k plus 1. Now the book has a misprint here. They have some problems with their subscripts there. Now, so a path is just a sequence of the vertices and edges, and you may not need to label the edges. If there's only one between two vertices, then you can just label the two vertices here. Now, a simple path is where all the vertices are distinct. Okay. Now, a graph, connected graph, whoops, wrong. Connected graph is one where there is a path connecting any two vertices. Okay, so you can always get from one vertex to another by a path. Closed path. In a closed path, we have our initial vertex is our final vertex. Okay. A circuit is a closed path of a particular type where all of the edges are distinct. I'll do an example here in a minute, but you don't go over any edge twice. It doesn't matter which direction, you're not going to use it twice. Okay. A cycle is a circuit. So it's a closed path where all the edges are distinct, but not only that, it's a circuit where all the vertices are distinct as well. So not only do you not travel over the same path twice, you don't find yourself in the same vertex twice. So let's do an example here. Here's the old graph I introduced earlier. Okay. It's got the 5 vertices and 9 edges as listed here. So here's an example of a circuit. Let's do different colors for a second. Okay. Circuit would be something like, well, it could be 5 to 2. So I won't put E4 down there because there's only one edge there. But vertex 5, edge, vertex 2. Then we're going to go to 1 by E1. Then we're going to go back to 2 by E2. Then we go to 3 and 2, 5. That's a circuit, but it's not a cycle because I'm in vertex 2 twice. Now, an example of a cycle that from 5 to 5 is a pretty simple one. Let's do from 5. There's a bunch of them. 5 going to 2 to 3 to 5. Okay, that's a cycle. It's a circuit because it starts and ends at this. It is a closed path because it starts and ends in the same place. It's a circuit because we're never going over the same edge twice. And it's a cycle because we're never going through the same vertex twice. Okay, here's some more terms here. Vertices are connected. Okay, and that would be, obviously, there's a path between them. Okay. Now, when you have connected vertices, then there's an equivalence relation. Let's not call it V1. Let's say V is related to W if there's a path. Okay, and so we'll call this relation J. We'll write it something like this. That's how the book does it. And you think J as being something like joined to. Okay, so V and J, W are going to be related. They're going to be joined here. So this becomes an equivalence relation. Okay. And this equivalence relation partitions the vertices into pairwise disjoint sets. They're equivalence relations, you may not remember from 305. They partition things into, we have one group here, this is everything that's equivalent to each other, then another group, and so on. So it partitions the set of vertices into pairwise disjoint subsets. Okay. And these disjoint subsets would themselves determine subgraphs. The subgraphs determined by these subsets are called components. Okay, down here I've got a graph. Let's scoot this up so we can play with it a little bit. And this graph consists of 8 vertices and 7 edges. But it's impossible. These 3 vertices on the left are related to each other because they are joined by paths. These 3 on the right, these 4 on the right are related to each other because you can get paths from one to another, and this one vertex down by the bottom is related only to itself here. Okay, so this particular graph has three components. And we'll use the following notation. Capital K of G is the number of components of graph G. Okay. And the thing to remember here that K of G is 1 if and only if the graph is connected. Okay. Okay, so we're looking now at paths here. And a path that's made up of k number of edges is called a k-path, a k-length path, or just a k-path. Theorem 431. Very good theorem here. Let A be the adjacency matrix for the graph. So remember that in the matrix A, the entry in row I, column J is a number of edges joining vertex I with vertex J. Okay, so if we have the adjacency matrix and we raise it to a whole number power, a to the k, then the ij entry in there is the number of k-length paths from vertex I to vertex J. Okay, got a nice example here in a minute, but let's try to prove this by induction. So, okay, so an inductive proof, we have to start by looking at the basic case, k equals 1. Okay, well, this is obvious, right? Because this is how the matrix, the adjacency matrix is formed. Because what I said before, the ij entry in a to the first power here is the number of single edges, or just edges, and an edge will be a one path. So it's a number of one paths connecting vertex I, vertex J. Okay, so in k equals 1 case is true. Now, inductive proof, we have to, next we do our inductive step, is to assume that this is true for the case k minus 1. In other words, the k minus first power has entries which are the number of k minus 1 paths from vertex I to vertex J. Okay. Now, let's take a look. Let's remember then that by matrix multiplication, a to the k power is a to the k minus 1 times a. Now, what is the ijth entry in a to the k? Well, remember how you multiply matrices. You'll take the row times the column. So this is row I of the first matrix times column J of the second matrix. So the ij entry here is, it's the sum from, say, p equals 1 to n of a sub I p, and I'm going to put this in parentheses, k minus 1, times a sub p j. Okay. Where a sub I p, the k minus 1 in parentheses, I just mean the ipth entry in the k minus 1 matrix. Okay. Now, remember what that means. This is the number of k minus 1 by assumption, our inductive hypothesis. This is the number of k minus 1 paths from vi to vp. Okay, so when you take one of these things, when you take this, okay, we're taking times a sub pj. Okay, now this is the entry in a. Okay, a sub ip k minus 1 is in k minus 1 power. A sub pj is in the first power. So this is the number of k minus 1 paths, okay, I to p times the number of single paths from p to j. So this is the total number of k paths, okay, from vertex I to vertex j, where vertex p is the next to last stop. Okay, now what we do is we multiply each of these things and we add them all up for all possible last stop, next to last stops. Okay, so in particular, when we add all of these things up, okay, we have k minus 1 paths and then 1 paths from all the different vertices that connect to j. Okay, and this equals the number of k length paths from vertex I to vertex j. Okay, so that's kind of a more or less an inductive proof here. I was a little short on some of the reasons. But so the interesting thing is, when we take our adjacency matrix and raise it to powers, we get great information. So as an example, let's go back to our previous 5 vertex problem here. Here's the adjacency matrix. So in particular, this 2 means we're going from vertex 1 in the first row to the second column to vertex 2. So there are 2 arcs connecting 1 and 2. So E1 and E2. Okay, so I took this to the third power, and this is the matrix I got. I want to take a look at this number 13 I'm circling here. This is in row 2, column 3, and this was a degree 3 power. So this means there are 13 paths of length 3, that's the exponent, connecting V2 with V3. Okay, now some of these are kind of strange paths because it would be 2 to 3, that's 1, around here, that's 2, and around there, that would be a path of length 3. Okay. It also might be 2 to 5 to 3, that's 2, and then around this one more time. Okay. So that's how you interpret it. Okay, more terms, many more terms. Okay. Bridge. Okay. This is, scoot this over. This is an edge in the graph with the property that removing it disconnects the graph. I don't have any edges and any bridges in this thing here. You'd have to throw out a fair number of things to disconnect this graph. Okay. Actually, you have to throw out like 2. If you threw out E7 and E9, that would disconnect the graph because 4 would be out on its own. So, okay, so a bridge is an edge with the property that if you remove that one bridge, you disconnect the graph. Okay. Acyclic graph is a graph with no cycles. Okay. Okay, a graph with no cycles. It's also called a forest. All right. And a connected forest is called a tree. Okay. So when you're talking about an acyclic graph, you're talking about something like this. There is no edge over here that would give us a cycle in this place. Okay, so here's an example of an acyclic graph. Okay, but it's not connected, so we're going to call that a forest. Now, a connected acyclic graph is just something like this, and that's a tree. Okay, we'll be talking more about trees here soon. Now, in the next section, we take a look at a lot of these things only in terms of directed graphs or digraphs. Most of the previous terms, you know, closed circuits, cycles, and things like that are very easy to define once we understand them for regular graphs. There's a few other things going on here, though. Okay, a directed path. Well, this is going to be a finite sequence of vertices and arcs. Remember, an arc is a directed edge here. Starting with a vertex and ending with another. Okay. I'm not going to write this down, but it would be V1, E1, and so on like that. Okay, a little bit of terminology. If a directed path starts at V and ends at W, we say V is connected to W, then V is connected to W. Okay. So if it starts in V and ends at W, we'll say W is connected not to V, but from V. So connected to and connected from. Okay. Strongly connected is the property you have when two vertices are connected both ways. In other words, if V is connected to W and W connected to V. So you can have a way of going from V to W and along a directed path, and a way of going from W to V along a directed path. Okay. Now, unilaterally connected just means V there is some directed path that connects one of these to the other. In other words, if V is connected to W, then W is not connected to V, then we can just say that V and W are unilaterally connected. That just says that there's a path, some kind of path going from one of them to the other one. Okay. Let's see, and we have the notion of a closed directed path that will start at the end in the same place. A directed circuit, there'll be a closed path that none of the vertices, none of the edges are all distinct, and a directed cycle is all the vertices are distinct. Okay. Now, for the undirected, the ordinary graph, we had a result about powers of adjacency matrices, and the same thing here. If A is an adjacency matrix of a directed graph, then the power A to the K, then in that power, the IJ entry is a number of K length directed paths from VI to VJ. Okay. So it's a very similar idea. It's just that these things have a direction. Okay. The next idea is the notion of an orientation. When you take a graph, if the edges of a graph G are changed to arcs, in other words, we're giving them directions, then what we've done is established an orientation on G. Okay, so I have one here. Let me enlarge these a little bit. Here's a graph G. Okay, and I'm going to establish an orientation on G. Let's see, let's do this. Nope, I'm on black. Okay. Let's, instead of just an edge joining 1 and 2, let's make the edge go from 1 to 2. Let's have the edge go from 2 to 3. Let's have an edge go from 4 to 3. 3 to 5, 4 to 5, and 5 to 1. Oops, I left out the 1, 4. Let's give it this orientation. Let's give it this direction. Okay, so I've established an orientation on G. Now, strong orientation is one where we make a strongly connected graph out of it. Okay. Now, is this a strong orientation? A strong orientation here. Okay. Well, the only thing I can see here is, well, this is strongly connected, or a strong orientation, in other words. The question might be, can you get from someplace like 2 to 4? Well, sure, you can go 2 to 3 to 5 to 4 to 1. So 2 is connected to, 2 to 3 to 5 to 1 to 4. Okay, so there is a path, a directed path from 2 to 4. And you can certainly go from 1 to 2 and to 1 to 3. You go 1, 2, 3, 1 to 4, 1, 2, 3, 5, 1, 4. Or actually, just go 1, 4. Excuse me, it's stupid. Okay, 1 to 5. To go 1 to 5, you go 1, 2, 3, 5. So 1's connected to everything. 2 is connected to everything. 2 is connected to 3, obviously. To 4, then we go 2, 3, 5, 1, 4. 2 is connected to 5. 3 to 5. 2 is connected to 1, 2, 3, 5, 1. So you can show that this is a strong orientation. There's a few other things I need to check there. And there's a way to look at this. We have a graph is strongly oriented if and only if it is connected and has no bridges. Okay, we'll look at this a little more later on. Okay, just about done. One more topic in this section, that's the notion of reachability matrix. So the reachability matrix of a directed graph, of a digraph, with n number of vertices, okay. It's the n by n matrix R, and it's going to be, say, a typical element, the ijth entry of the matrix, where the ijth entry matrix is 1 if there's a directed path from vertex I to vertex J. And 0 otherwise. Okay, well, let's do an example. And we'll do a reachability matrix in this example. Okay, I have a graph G consisting of vertices and edges. The vertices are 1, 2, 3, 4, 5, 6, and the edges are 1, 2, 2, 3, 3, 4, and so on. This is a directed graph. Because these are ordered pairs. If there was just a set with 1 and 2, then it would be how we write down an ordinary graph, an undirected graph. Okay, so we're looking at ordered pairs here. Okay, Okay, I have yet to get, there we go. Okay. So I have 1 to 2. Let me put in the edges and I'll come back and make arcs out of it. Oops. 2 to 3. Arcs just means I put arrows down there. 3 to 4. 4 to 5. 5 to 6. Then 1 to 6. 2 to 6. And 5 to 2. So an edge from 1 to 2. 2 to 3. From 3 to 4. 4 to 5. From 5 to 6. Then from 1 to 6, from 2 to 6, and from 5 to 2. Okay, so there's the directed graph that goes with this guy. Okay, so let's answer some questions. Find a 6 path from 1 to 6. So I want a path from 1 to 6 that takes 6 edges. Okay. Well, I'm just going to write down the vertices in order since I don't have multiple edges here. It's going to go from 1 to 2 to 3 to 4 to 5. So 1, 2, 3. Okay, so that's 4 edges. Now we go to 2 and then to 6. Okay, so 1, 2, 3, 4, 5, 6. So there's a 6 path. Okay. Now part B, we want a simple path from 1 to 6 that uses 5 arcs. Just go around the edge here. 1 to 2 to 3 to 4 to 5 to 6. That is 1, 2, 3, 4, 5 directed edges. Okay, another simple question. Find a cycle with 4 arcs. Well, there's several of them here. But there's the one that goes 5 to 2 to 3 to 4 to 5. Okay. Now, part D, we're interested in figuring out the number of 2 paths from 2 to 4. So what I'm going to do is to make up my adjacency matrix. Excuse me. And then raise it to the second power, because powers of the adjacency matrix count number of paths connecting the vertices. Okay. So, and again, the grids here is just to help me keep things straight. So first row, first column, there is no arc from 1 to 1. There is an arc from 1 to 2, nothing from 1 to 3, 1 to 4, 1 to 5, but there is one from 1 to 6. Okay, 2, nothing from 2 to 1 or 2 to 2, but 2 does go to 3, not 2 to 4, but 2 to 5, yes, and, excuse me, no, 2 to 5, no. So 0, 0, 2 to 3, 0, 0, 2 to 6. Okay, now we're headed out of vertex 3. 3 doesn't go to 1, 3 doesn't go to 2, 3 doesn't go to 3, it does go to 4, but that's it. 4, there's no arc from 4 to 1, or 4 to 2, or 4 to 3, or 4 to 4, but there is from 4 to 5, but not 4 to 6. And 5, okay, there's no arc from 5 to 1. There is one from 5 to 2, but 5 to 3, nope. 5 to 4, nope. 5 to 5, nope. 5 to 6, yes. And finally, 6, no arc comes out of 6. So that's just a row of zeros. Okay. So there's your adjacency matrix. Now, 2 paths. We're going to look at the square of that. That's why I already have the square written down here. And I've done that. It's a pretty sparse matrix here. If we're looking at two paths from 2 to 4, so I start here at row 2, go to column 1, 2, 3, 4, and there's only one. There's only one 2-length path starting at 2 and going to 4, and that's the one that goes 2 to 3 and 3 to 4. Okay. Now, finally, I've got to do the reachability matrix, and let me bring this thing down here a little closer. So the reachability matrix is the entries are 1 if it's possible to get a directed path from row I to row J, the vertex, and 0 otherwise. Okay. Is there a directed path from 1 to 1? Nope. Okay. Is there from 1 to 2? Yes. From 1 to 3? No. Excuse me. I'm not doing this right. Okay. Is there a directed path from 1 to 1? No. Once you leave 1, you can't get back in. 1 to 2? Yes. 1 to 3? Yeah. 1. You go from 1 to 2 to 3. 1 to 4? Yes. 1 to 2 to 3 to 4. 1 to 5? Yes. And 1 to 6. Okay. 2 to 1? No. 2 to itself? No. Excuse me. I'm looking at this wrong. I'm still thinking in adjacencies. Is there a directed path from 2 to itself? Yes. 2, 3, 4, 5, 2 is the directed path there. 2 to 3, yes, obviously. 4, obviously. 5, yes, and 6. Okay, 3. 3 to 1. Nobody, you can't go into 1, so there's a whole column of zeros there. 3 to 1. 3 to 2, yes. 3 to 3, well, 3 to 2 is 1, 2, 3. 3 to 3 would just be going around to the next one more time. 3 to 4, obviously. 3 to 5, yes. 3 to 6, yes. 4. 4 to 1, no. 4 to 2, yep. Go to 5, then to 2. 4 to 3, yep. Go to 5, 2, then 3. 4 to 4, well, just another tick on the going around there. 4 to 5, obviously. 4 to 6. 5 to 1, no. 5 to 2, yes. To 3, yes. 4, yes. 5, and 5 to 6. Now 6, no arrows lead out of 6. So there are no directed paths starting at 6. So the reachability matrix is a row in the first column, and the bottom is 0 in the first column and the bottom row, and everything else 1s. Okay, well there's section 4, 3, and 4.